Solving math problems can often feel like an elaborate and potentially mind-bendingly difficult search for the twisting and winding path from A to B. For example, if given two non-equal line segments, we can multiply the shorter one by some number n to give a longer product than our original longer line segment. From this, we might seek to show some infinitely repeating decimals are actually equal to non-repeating decimals or even whole numbers through a series of potentially very strange and abstract logical steps. But what if, instead of looking for that path, we changed our perspective a bit to first get a lay of the land? Much as one might do when traveling on foot. Would we notice that, mathematically speaking, our starting and ending points are just not in the same space? Maybe none of the operations that we are equipped with will take us there. In other words, we can show that B is out of reach of A. This might seem like a defeatist attitude, and yet these sorts of conclusions are not only commonplace in math, but also often just as illuminating as their affirmative counterparts. As just one example, the knowledge that e and pi are non-algebraic, that is to say that they cannot be reached through the solution of a very broad and well-behaved class of equations, is in and of itself deeply fascinating. It says something more fundamental about these numbers than a great deal of other results about them, elevating them to the class of transcendental numbers. So this is a video about reachability in math, broadly stated, a behavior which leads us to a technique we just briefly saw. Proof by cases. We will explore how this concept comes up again and again across vastly different fields of math, often dressed up in different ways, but addressing the same basic question. Can we get there from here? And the related, extremely useful question, if we can't get there, what are we missing? Hopefully, by the end of the video, you will see how you can adapt this idea to solving math problems of your own, creating complicated looking problems which can secretly be solved really fast, and even such strange ideas as crop circles. Mysterious. Now, before we really dig into the many different examples of reachability, I have to point out a bit of a harmless but important technical detail. Reachability isn't really real. Huh? Then what is this video about? Well, you see, when I say that it's not real, what I mean is that reachability is not a strictly defined mathematical concept in as broad of a sense as I'm using it today. It is defined in, for example, control theory, which you can find a lot of results about, and if you look up accessibility, a related idea, you might chance on an odd result from number theory. In this video, we will be in fact examining both of these concepts and more, since they ultimately, as I hope you will soon agree, carry the same principle at heart. This is what I'm calling reachability. As I mentioned before, reachability dresses up in different ways and in different places. With that out of the way, let's begin. We start with a problem which you may have heard of before, set in a slightly new way, the chicken MACnugget problem. The problem, or rather a closely named relative, has seen some coverage on YouTube in the past. If you haven't heard of it, great. If you have, then you may likely have heard of the Frobenius number. We will first state the MACnugget problem, then take a look at how a much simpler, helpful problem will show us just how to use the key idea of reachability to derive the Frobenius number of our MACnugget boxes. So what is MAC? Why, machine-activated chicken, of course. MAC is a fast food chain which prides itself on its automation practices. Every order is carried out entirely between customer and machine. Recently, you, as an engineering consultant, have been hired by MAC to deal with a particularly annoying problem. Although MAC machines allow customers to order any custom amount of their popular MACnuggets, these little treats are still pre-packaged in boxes of sizes that we call A and M. When a customer orders, the machine simply spits out the correct combination of boxes. Unfortunately, recent customers have been breaking machines, perhaps deliberately, perhaps not, by inputting MACnugget orders in which the sizes fry the circuitry. The worried management seeks an admittedly stopgap solution to this problem by imposing the minimum MACnugget order, making it impossible to order all the system crashing combinations. Your job is to find out just how big that order is. You might think of these numbers, A and M, the sizes of our McNugget boxes, as the starting point, and all the numbers greater than or equal to the Frobenius number of A and M as the ending point. Quite a daunting task to find all of these combinations which form that path. Try to think of a few of these combinations. Are you seeing any patterns? As promised, we'll come back to the solution for this problem after looking at a simpler problem with the same ideas. Now, for another dreary workplace example, suppose you work at an office where the management has decided to take some unusual measures to, quote, improve workplace efficiency, unquote, by cutting down on the number of light switches. Strange, I know, but what do you expect in today's economy? The way this has been achieved is by wiring each switch to 2 lamps, so now a single flick of the switch causes 2 lamps to switch states. That is, an on lamp will go off, and an off lamp will go on. Contrast this with a normal switch, which does the exact same thing, but with only 1 lamp. Now, normally, this is at worst a quirky nuisance, until one night, oh woe is you, you are the last to leave the office. The only light on is at your desk, and so you have to turn off all the other lights. But with this newfangled switch system, it's honestly pretty hard to pin down the right combination. Try turning off different lights, see what happens. Trial and error seems to take us tantalizingly close to the real solution, but then that's hardly much of an improvement, given where we started, remember, with only 1 light on. At this point, if you are feeling particularly introspective, you might start trying to remember if you've ever seen all of the lights off around here. For that matter, have you even seen them all on at the same time? It always feels like there's a light on or off somewhere. Let's think once again of our problem as that path from A to B. Consider all the different switch flips we can do. These arrows represent them, but why only 3 or really 2 arrows? Well, consider what can happen when we flip the switch. It becomes apparent that the boundary we set between the even and odd numbers is no accident. We see that no matter what switch we flip, we cannot escape the odd numbers. We do not have anything like this. So our goal of turning off all the lights is, unfortunately, unreachable. You'll just have to hope that no one notices the odd light on in the morning, as they haven't for a long time now, presumably. But now, back to our original problem. Is there some way that we can separate the numbers into categories to determine whether or not there is such a maximum unreachable order of MACnuggets for our A and M sized MACnugget boxes? As you might expect, the answer is yes, and in a way quite similar to what we just saw, though with a few twists. When we were dealing with flipping switches, we saw that no matter what our choice of flips was, we stayed in the odd numbers. Or, to put it a different way, we stayed in the numbers whose remainder on dividing by 2 was 1. We could also call this a congruence class modulo 2 represented by 1, or C1 for short. The reason we say represented is that, of course, C1 equals C3 equals C5, hence odd numbers. All of these numbers represent the congruence class to which they belong. Let's apply this congruence class idea to M, the larger of our MACnugget box sizes. As we might expect, where odd and even gave us 2 groups of numbers, that is to say those congruent to 0 modulo 2 and those congruent to 1 modulo 2, we now have M such groups, that is to say those congruent to 0, 1, all the way up to M minus 1, where every number falls into only one class. So once again, we've broken down the problem space into multiple distinct categories, a good start for proof by cases. But what next? Well, we're going to make use of a very clever trick involving A, the smaller MACnugget box size. Watch what happens as we multiply the different class representatives by A. Amazing! No matter what set of representatives we pick, we always end up with a complete set of congruence class representatives modulo M, of course. In other words, multiplying by A shuffles the classes. Now there is a bit of a caveat with this trick, which we will discuss and see why it is not particularly relevant quite soon. But until then, let's just see how powerful our new approach to the situation is given this trick. As we have seen, every number fits exactly into one congruence class, of which we have M. Let's remind ourselves of what every number in a given congruence class looks like. That is, every number in this congruence class can be written as the remainder plus some multiple of M. Pause if you need to double check that this makes sense. We're very close to the result and things are going to start coming together quickly. And now, time to make use of our trick. Wow, just like that, things start falling into place. Now, by the same logic as above, we've arrived at a representation of every number as some combination of multiples of a with multiples of m. Now, when both of these multiples are positive, that corresponds to some actual number of boxes, and clearly that's reachable. This means that this entire part of the number line is reachable. Incredible. But what about when the multiple of m is not positive? Are those numbers reachable? Well, we can quickly see that at least in some cases, it's obviously not. I mean, when r equals 1, it's just a minus m, and a is less than m, so we get a negative number. Let's very quickly show that these kinds of numbers are in fact never reachable for any r value. Here we are going to once again see if we can find some way to separate our starting point, that is ra minus sm, from our ending point, which we will represent as ba plus cm, just for some reachable combination of MACnuggets. These labels come from our original definition of the congruence class. If we add sm to both sides and divide through by a, we get r equals b plus c plus s times m divided by a. Now, that's a bunch of variables added together and divided and hardly seems simpler. But the key is that since all the numbers involved in this equation are positive, we have that r is greater than b. Remember that since b and r are both numbers less than m minus 1, this necessarily means that this number right here, ra minus m, for each congruence class ra, is the biggest unreachable number. So then, what is the biggest unreachable number of them all? The minimum MACnugget order. Drumroll please. We end up with am minus a minus m. Splendid. Now we have the Frobenius number of any two numbers, right? And we can go back to the boss and input that quick fix, am minus a minus m. Well, yes and no. See, and this is where our little trick from before comes in. We can actually only use this formula if the two numbers happen to be relatively prime. That is to say, they have no common divisor. However, this is not so bad, because if the numbers do have a common divisor, then there's simply no minimum MACnugget order. So there are infinitely many unreachable points, making it less relevant to us and uninterpretable in terms of a Frobenius number. If there exists a common divisor, then our steps or combinations towards these reachable values are confined in much the same way that the switch flips were in our earlier light bulb example. We always stay in the same lane because once again we have no diagonal arrow, as it were. Hold on to these arrows, by the way, because they make a nice segue to our next destination, a tour of the applications. We have now seen that the implementation of the reachability idea from start to finish helps us with several problems, showing us both how we can derive a solution from breaking the problem into different cases, and how we can understand both how and why our solution fails, as in that example with the common divisor. We can now start applying the same idea to all sorts of different problems. As promised, those arrows are now coming back. If you weren't familiar with linear algebra before this video, then congratulations, you've got the basis. Haha. But seriously, it's no coincidence that our arrow analogy in the light bulb and the MACnugget problem worked so nicely. Here you can see how the number of vectors you have determines the points in space you can reach. Literally. And much as we could express all points in all congruence classes with two relatively prime numbers, we can express points in all of space with two linearly independent vectors. If two numbers have a common divisor, then they are restricted from infinitely many numbers. The same is true for two linearly dependent vectors, whose span might be thought of as the space reachable by their divisor. Vector space is also where the term reachability actually originates from. Control theory, as we mentioned before, which deals broadly with how to control some process in such a space, describes a point as reachable if some controlling vector can be used to take some dynamic system to that point. Of course, that controlling vector may also just be zero. The system might go there on its own. We can see here an example of just such a control process occurring on the trajectory of a spaceship. Now, moving through space is nice and all, but what happens when we deform space? What makes some spaces the same as others, even if they look different? Topology deals with these questions. We have highlighted 4 different sets of points on this rectangle. And though they obviously correspond to some distinct categories within the rectangle, it might seem unclear why we would call these four distinct sets equivalence classes. Notice the similarity to congruence classes. In fact, congruence classes are a special instance of equivalence classes. These highlighted sets are all of different sizes, ranging from 4 to infinite times infinite points. So what makes them kind of the same? Now we can see that this equivalence means equivalence under folding. The physical intuition is relatively simple, but the math can get kind of gnarly. Consider taking a few random points from this plane and asking where they will wind up under the make-a-torus operation. The calculations could be quite tedious, though with a bit of linear algebra relatively straightforward. On the other hand, if you check which equivalence class these points belong to, you can quite quickly determine which region of the torus they'll wind up in. And while this is all well and good to talk about for readily visualizable 2 or 3D space, it can be significantly more helpful with much more complex or higher dimensional spaces. Now you may have noticed, especially in the topology example, that breaking space up into classes often involves a sort of symmetry. In fact, the idea that there are these natural divisions in any kind of space and that certain actions do or do not alter these divisions is very much what symmetry is about. Consider the example of the mirror. A point and its mirror image are certainly distinct points in some sense, yet we have an intuitive, strong sense that they are the same in some way too. Many natural processes, such as flow, very broadly speaking, both of liquids and gases, are invariant, that is, they do not change under such symmetry operations. In some sense, the act of mirroring a set of conditions fails to reach outside of a certain equivalence class of points. Take a simple example. Consider standing 5 feet away from an unshielded light bulb. You don't need to specify whether you're 5 feet north or south or west. The light intensity, at least under ideal conditions, will be the same. That's rotational symmetry, and the points are sort of equivalent to each other. In their book, Fearful Symmetry, Ian Stewart and Martin Golubitsky provide an intriguing example of how symmetry causes certain unusual states to be reachable or not in nature. Specifically, using the example of crop circles. In particular, people have many often fantastical explanations about how crop circles form. In our terminology, we might say that people cannot see that the crop circle state of the field is reachable from the initial untouched cornfield state. But in fact, as Stewart and Golubitsky put it, don't be unduly impressed that corn circles are circular. A theoretically infinite plane of highly uniform corn can be shifted and rotated any number of ways without changing appearance. That is to say, it has a lot of translational and rotational symmetry. Suppose, however, that a small disruption, maybe a strange gust of wind or uneven soil, causes the translational or shift symmetry to break. The way that such a disruption spreads through the surrounding corn may very well follow the other unbroken symmetry, rotation. This is exactly what happens when a stone falls into water, breaking the translational symmetry of the flat water plane, but releasing rings. The disruption spreads radially until the rings peter out. This is quite similar also to disrupting an infinite plane of darkness, spooky, with a light bulb disruption, as we saw in the light bulb rotational symmetry example. Now granted, a conclusive physical cause for crop circles is not established, but the key idea is that whatever this cause may be, it takes us from one rotationally symmetric state to another, and it is perhaps more unlikely that such a disruption would cause an asymmetric state to form, that is to say, a state that isn't circular or something like that. So where does this all leave us? Ultimately, as the great mathematician Poincaré pointed out, mathematics is the art of giving the same name to different things. And I think this makes a great tagline for this video. Starting with some interesting toy problems in number theory, we have followed the idea of reachability through linear algebra, topology, and even into the somewhat paranormal. At the core of reachability, as we have seen, lies the separation of a problem space into distinct pieces, hence also this idea of proof by cases. On a very grand scale, the reason this technique is so pervasive is that math as a whole is built around the idea of sets, perhaps at the lowest level. One could even argue that breaking things into sets and understanding these sets is all of what math is about. Just think of a few of the most common synonyms for set. Apart from set theory, we also have group theory, category theory, scheme theory, and the list goes on. The concept of reachability as this passage between different sets is sort of baked into math at the core. I hope this video, with all of its jumping around and mashup of rigor with hand waviness, has shown you how we can reach for certain conclusions and ideas in math. Try to see if you can rephrase any particularly tough problem you've seen in a reachability framework. It can be surprisingly enlightening. I know it certainly changed the way that I looked at plain old evens and odds, but if nothing else, I hope that I leave you with the idea that in math, as in many things, when you're going from point A to point B, it helps to know the shape of the roadway.